now we move to questions, about 20-minute Q&A. So please raise your hand. Janendra, would you like to go first?
Yeah.
Go ahead.
So I have a question for Moty. So this is related to just a clarification of the statement on the last slide, where it says that the Fano factor is equal to the filling factor. So just to make sure, suppose we change the filling factor on a given plateau. In that case, does the Fano factor change with the filling factor, or does it remain pinned at the value given by the quantized Hall conductance? So is that something that you have looked at, or is it something that it can be determined within the experimental accuracy?
Yeah, that's a good question, Janandra. I think that I don't think that we scanned the plateau, but I think we made so many measurements that we are bound to be on different places on the plateau.
Okay.
And since we always get the sort of, I agree that the filling factor changes on the plateau, and I talk about the, the filling factor, and not the plus minus epsilon, but we did it so many times. So I think there is, I assume if I get out of the plateau, something might change, but it's a good point that we can try. We can think about it. We didn't study it.
So don't hesitate to raise your hands. So I have a question to Andrea. Is it possible to consider the case where boundary is curved, and what's the, to make it, to see the, what's the effect of boundary being not a perfect, not round?
Yes, the point is that I can compute something, but you have to give me an answer state. So the algebra is too complicated to get the entire spectrum. So you have to. That was what I was saying. If you are able, for example, to introduce some trial state that breaks rotational invariance,
yeah,
and creates, for example, a quadrupole or a multipole fluctuation of the boundary, then with this, my approach, I can compute the shape, I can compute the energy. So the question is to find the proper low energy state. So you see, so the one I have, the one I discuss are excitations within conformal field theory. So the kind that they don't break this rotational symmetry of the droplet.
Mm-hmm. I see. So I'll go just by the alphabetic order. So Sasha Abanov, go first.
Okay, when it comes to alphabetic order, I can beat almost everyone.
Yeah.
Okay, ciao, Andrea. Nice talk. Thank you very much. I have a clarification question. So you talked about edge reconstruction. So if you take some particular, not simple edge, but edge with few edit modes, what does it correspond in terms of W infinity representations? So is it some new representation? So can you clarify?
Yes, what I discussed, what I did is integer or Laughlin states, in which you basically conformal field theory is just one mode. Okay, then it's a Latinger limit with one component. Okay, so then you can describe the splitting of a droplet with 1/3 or 1. Okay, to discuss a more complicated droplet, you have to extend my analysis to multi-component abelian. It can be done, and the algebra is the same, but representation is more involved. So it's
so this would be another representation of W infinity.
Yes, like conformal field theory. Conformal field theory, the algebra is the same, but it can be realized into theory with the central charge 1, which has one mode, central charge 2, which has 2 modes, and so on. Okay.
Are these all irreducible representations?
Yeah.
Okay. Okay, thank you.
The point is that in conformal limit, the algebra is simple. I can diagonalize and get the entire spectrum, and everything is exact. Here, the algebra is complicated, so I'm bound to answer states. Okay, and so you give me an answer state which capture the right fluctuation. For example, Papich talk, and you write for me this state, and I can compute. That's the idea.
Okay, thank you.
Gabor?
Okay, thank you, Semyon. So this is a question for Moty. First of all, congratulations for the Buckley Prize. It's a bit late, but so I have a related question. Perhaps this answer is already out there. You know, I apologize. I don't, I don't work on this topic. So nowadays we have samples in which, let's say, the 1/3 state develops at low temperature, and then you heat it up in your dilution fridge and you can make it go away. So, think of some kind of a low density sample. And what would you then see for your shot noise as function of temperature? Would the 1/3 just morph into 1, or your technique maybe cannot apply in that case? What would you expect to see if, let's say, there is no data?
Moty, your mic is off.
Just unmute yourself, please.
Okay, I'm sorry. If you sit at 1/3 and you warm up, then the state disappears and the bulk is not anymore incompressible. And I don't think there is edge modes at all. I don't know what to tell you, because you will not measure any particular. Might not be any noise at all, or maybe the RXX will not be 0. There will be some Johnson-Nyquist noise or something like this. It's like a resistor. I don't think that I'm expecting to see anything.
Right, but this, if you kind of plot, say, the shot noise versus, temperature, I guess it's gonna you could just expect basically to gradually go away, you're saying, once the resistance lifts up from 0, RXX non-zero.
Well, the noise will have this temperature correction. It's a Kotanges hyperbole of something that depends on voltage and temperature. So it will flatten out more and more, and you have to go to higher and higher voltage to be a few times more than KT to get this straight line. And then at some point, maybe if there is a gap still, you'll be about the gap, so I don't know, because I know that when I measure E/3 and I measure it even at 100 millikelvin or something like this, because the state has a large gap, and you can increase the voltage, the applied voltage on the quantum point contact quite a bit, you do get 1/3 all the time. But I didn't continue until I break it down.
Okay, thank you.
So who would like to ask a question? I see, Don, it's you.
Yeah, so I want to ask one question for the experiment talk. I want to ask if you just change a little bit the contact from the boat to the sea, do you see the Fano effect, the Fano factor of the filling fraction of the sea, not the boat?
No, if you look, there is maybe I didn't understand your question, because there is a different filling factor between the sea and the boat. Okay, so there is an interface. You can move on this interface a little bit right and left, but this is already similar to what Janandra Jain asked about how the funnel changes when you move on the plateau. But if you move away totally from it, then you don't have any more edge mode. If you make them equal, then you're sitting in the middle of a new bulk. There's no edge at all. But maybe I don't understand your question.
My question is, now you have the contact, the measure contacts in the boat. What happens if you just move the contact a little bit to the sea? What do you expect for the noise measurement?
No, because okay, our contact sitting on the edge.
Okay, so it's on the edge.
On the edge, yes, because we are injecting, we are heating up edge modes. So we are sitting here, we sit on the edge mode itself, on the interface itself. And if you move away, then you're sitting somewhere in the bulk of the sea or the boat, and you don't see the edge there. It will be like a Corbino. You sit in only contact middle of bulk.
Okay, thank you.
Jiu Liu, if I pronounce correctly. Go ahead.
Thank you. I have a question for Professor Heiblum. In the talk, you mentioned we could measure the excitation of neutral modes use the hotspot at the backside of the source. I want to ask, how does that compare to the skin with a QPC with partitioning of neutral modes?
Oh, yes. So the initial measurement, if you say the very first paper that we discovered neutral mode, we ran the neutral mode into a quantum point contact, and we call it fragmentation, and we measure shot noise as a result of this fragmentation. But as time went by, we found out that you can, and then you have the neutral came in and it was excited. But where is it excited from? It was excited from some hotspot somewhere far down the line. And then we found out that even if you open the QPC and you don't partition it to the QPC, you don't fragment it to the QPC, but you go directly into an ohmic contact of an amplifier, also you get noise. The noise are not the same size because the mechanism is very different. But the group of Yuval Geffen already wrote more than one paper explaining how this neutral mode coming to an ohmic contact that is full of the amplifier followed by a ground after, upstream I mean, and how does it happen that you have this electron hole pair that jump around the amplifier and provide and give you noise. Okay, so if you look at the paper of Geffen et al., a recent paper in the last year or two, you will see a detailed explanation.
Does that measurements give you the same channel factor?
No. This is proportional to temperature the neutral mode came from, and there is no Fano factor there whatsoever. I mean, there is some property, I think, there of the edge, and we can find out from there thermal conductance, if you wish, by calibration or so, but I don't think that you see any information about the charge.
Okay, thank you for the explanation.
Okay, any more questions? All you would like to know about the edge modes, theoretically or experimentally? It's your chance.
Sorry, what was the question?
No, so far no question.
Okay.
So far no question. We have still about 7 minutes to the next talk. I don't see any raised hands. So to raise your hand, you go to reactions and raise your hand. Aha, I see from some. Go ahead.
Andrea, are there any calculation you can do with the Fabian state?
Yeah, I think I can do that. Yes. I mean, there is a problem to incorporate this W infinity. You cannot you cannot write it immediately for the Pfaffian state because central charge is 3/2, not integer. So you have to go through some kind of projection that I explained some years ago, and this projection basically consists in assuming first that you have 2 layers of different electrons that they have an additional degrees of freedom, and then you somehow symmetrize with respect to this, and then you go from a 2-component abelian theory to the Pfaffian. So 2-component abelian theory I can describe with W infinity, and then presumably I can also describe the Pfaffian through this projection. And but it has to be done. I mean, in principle, yes, but in practice, I don't know if I can go through all the steps.
Thank you.
Mansoor?
Yes, I have a question for Moty. It seems that theorists don't have an explanation for why the bulk is doing affecting this charge that we're talking about. You have most experience, I guess, as an experimentalist over all these years. Do you have yourself any intuitive feeling for why or what could be going on?
No, I don't. I think that the explanation that we have now by these, particles, I mean, partitioning and fragmentation together, that gives you always the bulk. So you need really neutral modes to be there, and we find everywhere neutral mode. And I don't know why other people say they don't have it. I think they have it all, but they don't see it because they are very short range, and they don't see them. But no, I don't. I asked quite a few theorists if they can come up with some, let's call it an Onsager relation for something like this that can show, and we don't have to do all this bin counting. Even talked to Charlie Kane at some point. He suggested to measure the charge, and he said, I have no idea, but I don't know if anybody tried. Okay.
Thanks.
Sure.
So anybody else? We still have about 3 minutes for another talk, for another question or two. Don't be shy. Go ahead. Raise your hand. Or just jump in with a question. Should I look at Discord, or Discord is for the after talks?
No, this is for after talks. So.
All right. Oh, I see a question from Duncan. Go ahead. But unmute yourself. You're muted.
Yeah. For Andrea, so the W infinity algebra is the same as the Gervin-McDonald-Platzman algebra, or is it an approximate? Is it a expansion? I mean, do you say the Gervin-McDonald-Platzman is W infinity, or isn't W infinity an approximation to it?
It is, but when you...
Is it synonymous with it or not, right?
Yes, but it depends where you represent this algebra, okay? And for a proper large droplet limit, which is also low energy limit, you have to go to this large n limit, and the large n limit, large number of electrons, the algebra get singular. And so the only way to make sense of it is to go through the edge physics, which is well-defined, has a well-defined limit. In that limit, you also discover that there is a central extension in the algebra that is a quantum relativistic effect. So that you wouldn't have expected before. So it's a matter of representation, okay? And the central extension is also a matter of representation of the space of states. And so my formulation of the double infinity I was showing you is a proper limit of the GMP algebra when you take large droplets.
Well, certainly if one takes, I mean, a semi-infinite droplet, yeah, I mean, a semi-infinite edge, right?
Yes.
I mean, that's when you can, I mean, in a sense, the proper conformal limit is the semi-infinite system as well, right?
Yes, yes, semi.
So to avoid the, remove the quantization for going around the edge, right?
Yes. You know, the central extension is a property of, and also the value of the Casimirs, the dimension.
If I expand,
depends on the representation, not on the algebra. And without representation, the algebra is useless. You can use to relate different observables, but you cannot compute one of them. You see?
So I mean, certainly there's one issue about one can regularize the GMP. The crucial thing for the GMP algebra is to regularize it by subtracting the background charge in the bulk, at least, right?
Yes.
And then it has an analytic expansion in powers of momentum.
Yes.
And so I'm just asking. So of course, then you have the expansion is in powers of the magnetic length. So the lowest order is L and then L cubed. So is the W infinity algebra just keeping the second term in the expansion in powers of the magnetic length, the cubic term?
I mean, the W algebra is a generic statement, so that depending how you realize this algebra on the space of states, all the terms beside the first one, which is a classical limit, may change, and also the central central term can change. So for example, you would like to think, I don't want to have a half space, I want to have an infinite space. Then you have to start quantizing on a torus, for example. On a torus, then you have to imagine to take this limit on large tori, where number of particles increase, so some quantity will explode with the number of particles. You have to subtract this infinity, which is a sort of background cancellation, and then you come up with something which is sensible. So this is something that has not been done, but for the droplet on the edge, this is done, and this is done by conformal field theory. You see, so in the semi-infinite, it has been done. I can use it. For the infinite that would correspond to, say, a torus, it has not been done. So what is the proper central extension of GMP algebra on the torus? Is not known. There are some elementary attempts in the past, but nothing special. You see?
So what's the central extension of the W algebra like? I mean, what is it? I mean,
it's the same. It's
different from the central.
It's the same as conformal field theory.
Okay, it's just a Virasoro central charge.
Virasoro charge, and then there is a factor which is known. Factor which depends on the higher spin that is known. So.
Okay, thank you. I'll read your paper.
Thank you.
Okay, so it's a good moment to start next session. Inti, are you there?